following diagram shows a rectangular area, ABCD, enclosed on three sides by 60 meters of fencing, and the fourth is a wall. Find the width of the rectangle and give its maximum area. So if we have this is x, and this is y, we have 2x plus y is 60, and we have x times y is the area. So now we have y is 60 minus 2x into the area, and we can find the x-intercepts. So if we set this equal to 0, we have x is 0, or 60 minus 2x is 0, which is x is 30. So that's like at 0 and 30, so the maximum is going to lie in between those. So 0 plus 30 over 2, which is 15. So that's the answer to A. And find the maximum area. So we're going to have 15 times, I guess this one, 60 minus 2 times 15, which is going to be 15 times 30, which is 450 meters squared. Okay, for number 9, a farmer wishes to create a rectangular enclosure, ABCD. Area is 525, as shown below. So if we have x and y, we have x times y is the area. So the fencing used for side A, B is 11, and the fencing for the other 3 sides costs $3 per meter. So this is going to be 11y. This is 3y, because that side is only y. That's y meters long, but those meters cost $3 a piece. This is also 3 times however long x is, and 3 times however long x is. Okay, so we have 3x plus 3x plus 3y plus 11y, and that's going to be the perimeter. So this is 525 rather. Okay, so now if we do y is 525 over x, we will have 6x plus 14 times 525 over x equals p. Okay, so this is going to be I think that. Okay, so then this is 6x plus 7,350 over x equals p. So then we need to find the derivative of that. So dp dx, which is going to be 6 minus 7,350 x to the negative 2. All right, and we want to find when that's a minimum, so we set it equal to 0. So we're going to have 6. So 6 equals 7,350 over x squared. So x squared is 7,350 divided by 6. And then plus or minus, but you know, it's got to be the positive. So that's 1, 2, 2, 5. That's x squared. So x is going to be 35. This would be with a calculator, I believe. So the minimum cost. So this needs to go back into this. So we're going to have, well, actually, to this one, or even better, this one. So 6 times 35 plus 7,350 over 35. I'm using a calculator. So 6 times 35 plus 7,350 divided by 35, which ends up being 420. That ends up being the minimum cost. All right, number 10, 2 cubes of edges x and y. The total surface area of the 2 cubes is that. So we're going to have 6 sides, and each side is x squared, plus 6 sides, and each side area is y squared. So then that's going to equal 300, and I will go ahead and divide by 6, so that is equal to 50. Okay, find expression of y in terms of x. So if we solve this for y, 50 minus x squared, and then I suppose we should do plus or minus 50 minus x squared. Given that there's a minimum value of the total volume of the cubes, find this minimum value and the corresponding dimensions of the 2 cubes. Okay, so the volume is going to be, x cubed plus y cubed. And if we want, so if we do, okay, first we need to substitute this side length in. So this is not going to be negative because it's a side length. Okay, so we're going to have x cubed plus 50 minus x squared, the square root of that, to the 1/2 in that cube. So this is going to be to the 3/2. Okay, so then we can do dv dx, and we're going to have 3x squared plus 3 over 2, 50 minus x squared to the 1 over 2 times negative 2x. Okay, and I'll just rewrite this. The 2's will cancel, so minus 3x square root of 50 minus x squared. And then this, we want to set that equal to 0 so that we have the minimum or max, the minimum value. Okay, so we can factor out a 3x, and that's going to be x minus root 50 minus x squared, and that's equal to 0. So x is either 0, which can't be, or x minus root 50 minus x squared is 0. So we'll write this like this, and then square both sides. Add x squared over, so that's 2x squared is 50. So x squared is 25. So x is plus or minus 5, but obviously we'll take the 5. Okay, so that is the x value for when there's a minimum value of the total volume of the cubes. Find this minimum value. So we need to sub back into this thing. So we're going to have 5 cubed plus 50 minus 5 squared to the 3/2. And then that's 125 plus 25 to the 3/2, which is the square root of 25, which is 5 cubed, so 125 again. So this is 250. That's the That's the minimum value of the volume. And the corresponding dimensions of the two cubes. So we've already got x is 5. And we have y is root 50 minus 5 squared, which is also 5. A closed cylindrical can has a volume of 250 pi. So right away we have the volume of a cylinder is pi r squared times the height, and that's equal to 250 pi. So r squared h is 250. The height of the can is h and the radius of the base is r, okay? So find an expression for the total surface area of the can. So this is volume, surface area. We've got two circles, top and bottom, so pi r squared each. And then we have the curved surface area outside, which is 2 pi r times the height. Okay, so this is the area. Now, in terms of r, so we have to solve this thing and put it into here to get area just in terms of r. So now we're going to have 2 pi r squared plus 500 pi and then over r, okay, because this cancels with that. Okay, so given there's a minimum value of a for r is greater than 0, find the value of r. So we need the derivative of a with respect to r. So that's going to be 4 pi r minus 500 pi r to the negative 2, which makes it on the bottom. Set this equal to 0. And then we've got 4 pi r equals 500 pi over r squared. The pi's will cancel. Cross multiplying by r squared, we're going to have 4r cubed equals 500. And dividing by 4, we're going to have 125. And that is going to be, the cubed root of 125 is 5. Because 5 times 5 times 5 is 125. So that's B. Show that for that can of minimum surface area, the height of the cylinder is equal to the diameter of its base. So we have the minimum surface area is happening when r is 5. So the height of the cylinder is going to be h is 250 over r squared using this. So that's going to be, the height is 10. And the diameter of its base, well, that's the diameter, is 2 times the radius, which is 5. Okay? So that's that. All right, the following diagram shows part of the graph of y equals x squared. So that's this one. And then g is 4x minus x squared, which is that one upside down. The two graphs intersect at 0 and a. Find the value of a. Okay, so this is a. So we've got 4x minus x squared equals x squared. So we're going to have 0 is 2x squared minus 4x, and factor out a 2x, and have this on the inside. So x is 0 or x is 4. So this is A. The vertical line segment is drawn between the two curves from 0 to A, where A is on F and B is on G. Express the length L of the line segment in terms of x. So we're going to have B, which is on the graph of G, is going to be, so this is the point, just some random x, and this is the y, 4x minus x squared. Okay, that point B is x, 4x minus x squared, just the general point. Okay, so that is the height of B, above. So L is going to be 4x minus x squared. And then from that, so that's this whole height here, okay? From the x-axis to B. So then if we want, so from that we need to subtract the height. So we've got this distance B from the x-axis, and we need to subtract this distance A. So we're left with from B to A is L, okay? So we've got the height of B. We need to subtract the height of A, which again we have x, and A is on this graph, x squared. So we're going to subtract x squared. So the length of L is 4x minus 2x squared. Find the maximum value of L, justifying its maximum. So we need dl dx, which is 4 minus 4x. Set it equal to 0. So 4 equals 4x. So x is 1. And we need to substitute that into the L. So we're going to have L equals 4 times 1 minus 1 squared minus 1 squared. Oh, I could have done it in here. Whatever. So 4 minus 1, which is 2. So that is the max value of L, justifying its maximum. So to justify, we need the second derivative, which is just negative 4. So that means it's concave down everywhere, actually. So x equals 1 is the maximum. All right, 13, a rectangle ABCD is enclosed between the x-axis, the curve y equals 2 root x, and the vertical line x equals 9, so that the lower vertices are on the x-axis with coordinates A, 0, oops, so A, 0, 9, 0, respectively, and D is on the curve, so this is going to be the point A, 2 root A. And the C is on the vertical line. So this is going to be 9, 2 root A, isn't it? Because it's on that same, it's the same height as D. Okay, so find an, so the area of this rectangle is denoted by S. Okay, so this thing, so think about it this way. We've got, this is 9, and this is A, so that whole length is 9 minus A. Let's do that. So like this, 9 minus A. So S, rather, is 9 minus A times the height, which is just 2 root A. Okay? So, yeah, that's fine, actually. Well, we might as well, because we're going to have to maximize it or something. 18 root A minus 2A root A, which is 18A to the 1/2, and this is minus 2. This is A to the 1, and this is A to the 1/2, so we have A to the 3/2. Okay. Find the maximum value of S. Okay, so we need ds dA. So we're going to have 1/2 times 9, which is, 1/2 times 18, which is 9. A to the negative 1/2 when we subtract 1 from the exponent. And then we're going to have minus 3. 2 times 3/2 is 3. A to the 1/2 when we subtract 1. And we want this equal to 0. So we're going to have 9 over square root of A minus 3 square root of A equals 0. And get the 3 root A over here, multiply by root A, which is just A. So A has to be 3. And we need the maximum value of S. So that goes back into here. So we're going to have 18 square root 3 minus 2 square root of 3 cubed. All right, so that's 18 root 3, and root 3 cubed is going to be root 3. All right, so you're going to have minus 2 times 3, which is 6 root 3, so 12 root 3 is the maximum value of S. Now C, write down the values of A for which we obtain a rectangle of minimum area S. So if we want a minimum value, basically we don't want a rectangle. So if A is 9, it's just a line over here. So that's going to be a minimum. And the other time that we have a rectangle this way is if the height is 0. So that's when 2 root A equals 0, which is at A equals 0. So those are the times you have a rectangle, not really, that has minimum area.